Testing. All right. Can you hear me? Can you all hear me? Hello, hello everybody. Let me just test this out. Hello, hello. Can you hear my voice? If you could, it would be great if you could let me know. All right. Okay, so hello. This is Junichiro Horikawa, and this is the 55th episode for Houdini Algorithmic Live. This is the weekly tutorial live that I'm doing for Houdini based on the algorithmic design concepts, mostly using Vex coding to do several design related stuff, including animation and modeling. And today's topic is to create this morphing motion graphics effect, which I'm gonna show it right now, using two geometry to morph between them through through a particle medium like these. And I'm going to show you how you could actually create this kind of morphing effect going from one object to another. Just by using a Vex code, since this one is not using any solver or anything. So it's not a simulation based stuff, but it's based on a procedural process just using Vex. Okay, so that's what I am going to show you today. All right, from scratch. All right, which could be really like useful because it's not really related. It's not using any solvers, which means is that by using this one, just to wait for a moment. This, since I'm not using any solver for this one, the good thing about this one is that let me see, you can go back and forth. Let me just delete this to 0 and this one to be 1. So you can just use those like something like sliders or frame bars to go back and forth pretty easily without any like generative or recursive calculations. So it's pretty easy. It's pretty fast with debugging. Okay. And since this is procedural, you can control the way it like blasts, changing from one to another by changing some parameters inside this code, the main code for the morphing. It's not that long. Okay, so I think it's pretty easy to understand what it's happening here. All right, so that's what I would like to tell you today. All right, so let's do it from scratch. I'm gonna start by creating the geometry node, and also let me save this so that I don't lose the process. Okay, turbulence morphing. So first of all, I'm gonna start by single geometry to test out how it should morph, and later on I'm gonna add another geometry for the target. Okay. Initially, I'm gonna start with the single one so that I can use this as a both for source and the target geometry. So any geometry is fine. I'm just gonna start with the pig head. Okay. And the initial things that I'm going to do is to scatter any amount of points on top of this surface, or maybe inside using a volume node or something. But I'm just going to use this scatter node to have a bunch of points on top of the geometry. Let's say I would like to have 10,000 points on top of the surface, like this. Now, next thing I like to do is to, I guess by using the scattering node, you'll be able to have a point randomly scattered on top of the surface, but just to make sure that it's really placed randomly on a surface, I'm also going to use the sort node to sort out the points randomly. Okay, so that you can move each point from a different location to a different target. So in for the final goal is to have another geometry, like let's say rubber toy, having the same number of points, and using a different seed for the random, and going from those points. One of the points corresponds to the points on the target and goes from one to another by using some turbulence related noise movement. Okay. And we don't really want to move those points linearly, which is pretty I don't know, too simple and too lame. So the goal here is to how naturally you can make it to morph from one to another, like a turbulence. Okay, so let's do that. I'm gonna keep the target as it here right now, and I am going to use the point wrangle to move all those points. Okay, so I'm gonna connect these randomly sorted out points to the first input of this point wrangle, and let's name this Turbulence Noise. And pretty much this is the Vex code or Vex wrangle that I'm gonna use to do all the stuff that I need here for today, for the stuff that I'm gonna show you today. Okay, other stuff is more of a visually related stuff to make the visual a bit more prettier, but all the logics, it's going to be written in here, and that is all. Okay, so let's start writing the code. Okay, first thing I would like to do is to the things that I would like to do here is to start doing the morph from, let's say, from top to bottom or bottom to top, or could be from right to left or left to right. By doing it, you'll be able to have a kind of a natural steps. So starting from top part, it starts to dissolve into a random particles or turbulence particles, and slowly all the particles on the bottom will be affected by those top particles, and after all the particles on top of this pig head being converted into a turbulence moving particle, then slowly I would like to make those particles fit into the target geometry in this case, the same pig head, maybe from bottom to top, or top to bottom again. Slowly start to show up the geometry slowly from bottom to top, or top to bottom. Okay. So what I need as an information initially is to have the bounding box information of this target or the source geometry. In this case, if I would like to morph from top to bottom or bottom to top, I need the y-directional values for this bounding box of this surface. So what I'm gonna use is to first use the get bbox function to get the minimum points of the bounding box and the maximum points of the bounding box from 0. 0 means it's the source geometry or the points. Okay, so 0 in max, and I need to create a empty variable for a vector to store the minimum and maximum point positions of the bounding box. Okay, now that you have got the minimum position, which could be somewhere around here, and the maximum position, which could be somewhere around here, and by retrieving the y component of this vector, you can get the minimum height, minimum y directional value, and the maximum y directional value. And you can use that to determine when those points should begin to dissolve. Okay. All right. So to dissolve, I'm going to create like a float offset value, which is going to be used as a frame value to determine when to start dissolving. Let's say I want to create this morphing effect from the first frame to the end frame, okay, and maybe using a 30% of the frame to dissolve from top to bottom. Okay, so thinking like that, you can first create some values which is in between 1 to, in this case, if it's 30%, it's around 60 or 72 frame, somewhere around here. Okay, so I would like to create a value from 1 to 72 and use that frame value to create a offset value. So for the top part, I want to dissolve, or I want to start morphing as soon as possible, like at around 1. But at the end point, on the bottom point, I would like to start dissolving these points somewhere around 72 and do it linearly. So if it's around 36 frame, the middle part of this geometry is going to be morphed. Okay, so I'm going from top to bottom. So thinking like that, I'm going to create an offset frame value using fit based on the y value of the point position, which is in between the minimum y and the maximum y. Okay, and let it be a frame value which is in between 1 to let's say 1 to, this is around, let's calculate this by the multiplication of f end. So f end multiplied by some morphing, let's say range, or gradient range, morphing gradient range. So if it's 0.3, then it's 30% of this end f end, which is 72. Okay. And let's see, this is okay. Okay, so I'm gonna start. I want to start from the top part. Okay, so maybe I should make it from top to bottom for a fit function. Then for the top part, I use 1, and for the bottom, I use this f end, frame end, multiplied by the gradation range. Okay, now let's promote those sliders and let's set it to 0.3 for now. You can change this later. And let's try this out if this value is really working. Okay, so to do that, I'm just going to try to move those points based on this offset value. Okay. Okay, so what I'm going to do here, let's see. Let's say I just want to move those points to the frame related value. Let's create a f value which is in between the first frame to the end frame, going from 0 to 1 by creating a fit function in a frame starting from 1 to the end of the frame and set it to 0 to 1. I'm gonna use this one together with this offset to move those points based on the frame. Okay, so to do that, I am going to let's say which is better. I'm just going to change this one to offset. Okay, so by doing this, you can start calculating. You can start having this f based on the y direction of this points. So when the height is around at the middle, it's not going to have it. The f values be kept as 0 until like 36 frame, and then at around 36 frame, then the f starts to raise up until the end. So let's see if that is true. I'm just going to check this out by, let's say, moving all the points upward by f related value. Maybe f multiplied by, I don't know, 1 is fine, I guess. So just f. Okay. Now I think I should do like this. Just add a f value to the y. So okay, so if I play it, you can see that gradually from top to bottom it moved like these from until 72 frame. Okay, so using 72 frame, or maybe I can multiply this a little bit bigger so that I can see the changes, and maybe moving to the x direction might be better. Okay, so check until from first frame to the 32nd frame. You can see that the particle is shifting based on the height together with the frame values. Okay, until 72, and after 72, all the geometry is moving at the same speed. Okay. So this is kind of a technique that I'm going to use to start set the timing of the dissolving or the morphing. Now I also have to do the same things for the end part, since if you look at the end, it stopped at the same timing. But what I really want to have is to stop by I don't know, maybe from the bottom to top, just like I did for the starting, using 72 frame to shift. And at the end, I would like to do the similar things, maybe using this same 72 frame to start stopping from bottom to top or top to bottom, somewhere around from 240 to 150 or 70. Okay, so to do that, it's not that hard to do. You just have to say add an offset to the f end for this fit function, but this will cause the maximum like f end value or the frame end value to be 240 plus 72, so you have to subtract by the maximum of this value, which could be this one. So let's have this as a variable float. Gradation range is this value here. And let's have this right here, and also have this gradient range here. Now let's see what's going to happen. Now for the first 72 frame, it shifts like these, and at the end, you can see that from top to bottom, it's start to stop shifting. Okay, just like that. Let's make this like 100 frames so that it's easy to debug. Okay, like this. Now instead of adding these values, you can also subtract, directly subtract the offset. In that case, you don't really need to subtract with the gradient range. So in that case, what would happen is that it stop from top to bottom. Looks pretty much, I needed to apply. So in this case, starts from bottom to top. So either way is fine. What I like is adding the offset and subtract by the grade range, since the total movement value is well kept the same in this case. Okay. Now that's the proof of concept. Now having this information, now I can start to have a bit more turbulence related vector values or forces to move the points. And to do that, I'm going to create some rotational values to rotate the geometry initially, and then try to add some noise onto the rotational angles, as well as some moving back and forth from the center to add a little bit of like noises, okay, based on this f value. All right, so let's do that. First of all, in order to rotate the points, I'm going to rotate the points based on the center points of the input geometry. So I'm going to get the bounding box center points first by saying vector center is equal to get vbox center, which is going to be the center point position. Okay, now I am first going to what I'm going to do next is to calculate the distance from the center to each point. And since I'm going to basically using the y-axis to rotate the geometry in this case, what I would like to do in order to calculate the distance, I would like to just calculate the distance on x z plane, and I don't want to consider the y directional distance. I mean, it could work, but that's what I would like to do because I'm rotating based on the y-axis. I really don't need the y directional distances. So in order to ignore this y directional distances, only consider the xz plane distance, I'm going to copy the current point position like this, and then set the y value of this current point position to the same y value as the center of this geometry, so that all the points that I have copied will be flattened to a 1xz plane. If you would like to check that, it looks like this. Okay, so it's been flattened like this, and from here I would like to calculate the distance from the center point to each of the point, and that is going to be the distance on the xz plane. Okay, so float distance is equal to distance position, flatten position, and the center. Okay. Now, and what I would like to use this for is for the angle for the rotation, in order to morph the geometry. Okay, I think I have some errors here. Flow dist is equal to distance. Okay, so let's calculate the angle. I'm gonna start by creating some simple angle values. Start by a pi, multiply by, I don't know, 2.0, and maybe multiply by f value. Okay, in this case, the angle will be set from 0 to a 2 pi from the first frame to the end frame. Okay, now let's try to use this angle to rotate the points. I'm gonna start by creating a rotational matrix. Start by creating an identity matrix, then use the rotate function to rotate the matrix using the angle and the y-axis, and then multiply this matrix to the points to see how the rotation works based on the f value. Okay, so let's set the real-time toggle. So as you can see, the geometry rotates from top to bottom using the 30% of the frame, and then goes back to the target geometry, which in this case the same geometry from using the 72 frame, like these. All right, now what I could do is to try to use this distance value to this angle somehow to see what kind of effect could it give. So if I multiply this distance to the angle right here, you start to see some, okay, maybe, okay, there might be a little problem, because if I use this distance as it is for the multiplication, it's not going back to the original geometry, so that's a bit of a problem. So let's try to avoid multiplying this distance right here, but use it for other purposes later. Okay. Okay, now at this point I might also want to control the timing of the rotation. It looks a bit hard when it starts, especially the edge of the rotation when it's rotating and it's still not rotated. You can see the change when it starts rotating. Okay, so I might not like that. So let's try to have a little bit of like dissolving, like smoothness when to start the rotation. Currently there you can see a line when it has started the rotation, but what I want to do is to have some kind of blur out the points, to pick random points near the edge, which one to rotate and which one not to rotate, okay, based on some threshold. So to do that, I might want to use some kind of I don't know, random values for that. So let's see what I could do here. Okay, so to do that, I think what I could do, let me think. I think I can basically these offset, the rotational offset or rotational shifting is done by using this offset value right here, which is in between 0 to, 1 to the frame value multiplied by 0.3 in this case. Now I could try to add some random values to this offset value, like random values in between 1 to 10 or 1 to 20 to this offset based on the, I don't know, the point position seed. Then in that case, basically the base rotational line is at this point, 72 frame right here. But by adding some constant random value, okay, in this case 33, by adding some constant random values to this offset for each point, you can kind of have a blurred edge where it starts rotating. Okay, so that's what I would like to test out here. So to do that, I can add some random related values. So rand at p and multiply by the maximum offset or random offset range. So let's have this as a parameter as well. Rand offset. Let's make this 10 for now. Okay, now that each offset value for the point has been changed, even when the y value is the same, the value has been offsetted a little bit based on this random values right here. I need to go back to this one right here as well to subtract by the maximum of this random offset, because in theory you are going to add maximum 10 to this offset, so you have to subtract by 10 for the final target or final goal for the fit function based on the frame. Okay, now if I try to look at here, you can start to see some bit more smoothen out, dissolving. You see there, you no longer see the edge of the rotation anymore, but you start to see random points going to pick. You still have a top to bottom like shifting, but by having this random values right here, you kind of see this dissolving edge of rotation. So by making this smaller, you have more smaller blurred edge. If you have a few frames, then setting this to a small number makes sense. If you have like a longer frame to do morphing, you might maybe having a lot of frames for this random offset might make more sense. In this case, around 5 to 10 might be good if it's 100 frame in total. Okay, that looks good. And as you can see, it's going to rotate from 0 angle to the 2 pi, which makes it go back to the same position. So I think it is always a good idea to make this angle a multiplication of 2 pi, which is 360 degrees. So I can have another parameter here as an integer, like as a rotation value, rotational like cycle. Let's name this rot cycle. So if it's 1, it's 2 pi. If it's 2, it's 2 pi, and so on. I mean, if it's 1, it's 2 pi. If it's 2, it's 4 pi. So if you have 5, then you have 5 multiplied by 2 pi, which you have a tons of rotations. Okay, let's set it to 1 or 2 for now. Okay, 2 might be a good. So it starts to have some effect that I'm looking for right here. Now it still has some kind of a linear rotational effect in terms of the speed of the rotation. So next thing I would like to do is to control the speed, especially for the starting and the end part. Okay, to do that I'm just going to use the ramp parameter to control this f value right here. So at the start I would like to make the rotation slow and then becomes faster, then becomes slower again to make it to the goal to the target particle. So f is equal to ch ramp. I'm gonna create some ramp parameter to map this f value, which is in between 0 to 1. Let's make it a Vizier, a B-spline, and create this kind of curve. So initially it goes slower, then goes faster, then slower again. Now let's see what happens. First it goes slow and stops slowly. If you want to exaggerate the effect, you can do something like these. Which could also be good, but I'm gonna keep it like this. Just a little bit of curve. Okay, starting to get a bit more natural here. Alright, now one thing I'm still missing is a bit of a turbulence noise. So next thing I would like to do is to add this turbulence related noise. And this is probably where I could use this distance that I've calculated previously. Okay, so let's try to do that. And to add a turbulence noise, I'm not going to touch the angle itself, but instead I'm going to try to move the points inward or outward using the center point direction and center point position together with the current point positions. Maybe creating a vector in between those two points and using this vector to move the points inward or outward after I have rotated the points. Okay, so let's try to do that. Okay, so to do that, I'm going to create some directional value, which is to, let's say I'm going to calculate the direction from the current point position to the from the center to the current point position, like these. And let's also normalize this. Oops. Okay. And then multiply this by some value in order to move out to define the distance, how much I want to move those points on outward or inward. Okay, and probably when the frame is at the 1 or a frame at the end, you want to keep the distance to 0. You want to make the distance value for the direction to be 0. So making some kind of mountain-like curve, like a sine wave curve, a sine wave value might make sense for this, for the multiplication value for this vector value. So based on the f value right here, which is going from 0 to 1 based on the frame value, I would like to first create a angle value for the sine function. So let's say sf is equal to a f multiplied by pi, and if you have this angle as a for the sine function, you'll be able to have a value going from 0 to 1 and going back to 0. Okay, like a mountain. Alright, so let's try to directly multiply this to this direction and also add this direction to the point and see what happens. So when it's rotating, it inflates the geometry and then goes back to the same target or the source geometry. Now the base is okay now, but just inflating this point with the same direction of same distance for each point is not that interesting. So let's try to use several like values to make it more natural or make it more turbulence-like noise. Okay, so first is to use like a noise-related value, which could be really straightforward. So let's name this noise mult or noise val using a noise function based on the point position. And this point position is the moving point position based on this matrix. So after the point has been rotated by this rotational matrix, I'm going to use that rotated point as a noise seed. But I'm also going to add another seed value, which could be a point position, the same point position, but the one that is not moving, which is before multiplying this matrix. So let's try to have a copy of point position again. Let's name this vector cpos, just like I did right here. Vector cpos is at p, and this is the copy of this point position which hasn't moved yet. And now I would like to use that cpos as a seed as well. And for this one, I'm going to multiply with the high value, which will create a bit of like higher noise or higher or more dense mountain value from 0 to 1. Okay, and then let's try to multiply this multi or noise value to see what happens. Okay, so this is currently the result multiplying this noise value. If I disable this one, let's see what happens. You see a bit more inflated looking like value, but by having this noise value, you'll be able to have a bit of noise surface. Now, if I try to disable this one, cpos, let's see what happens. You still see kind of inflated surface like these, which might not be really fun for myself. So that's kind of a reason why I added this additional seed value right here. And the reason why I'm using this position which is not moving as a seed is because if I try to multiply this point which is moving, then when animating you have a lot of jittering, or you have a lot of the movement of the point becomes not smooth anymore. You see? So this point position is kept as multiplied by 1 to make the movement smoother, and this cpos multiplied by 100 is to make the initial the state of the points to be randomish like these. So this is for the animation, this is for the state, the current state. Since this cpos is not animated based on the frame, that's the reason it's possible, why it's possible. And the animation becomes smoother in this case. Now, I might want to move in inward as well. Currently it's going outward only, so to make it go inward as well, you can subtract this noise value by 0.5 so that the range of this noise value becomes from negative 0.5 to positive 0.5 and becomes much better. Right? Now at this point you can try to have, or you can try to use this distance value that I have created a long time ago. And let's see how I can use this. First thing I could try is to multiply all these noise value by the distance and see what happens. This kind of exaggerate the outline of the geometry, which could be interesting. Without the distance, let's see what happens. Without the distance, it becomes more randomish. With the distance, you have a little bit of sharpened edge. Okay. Maybe I could try using a power function to exaggerate more, to have more edges, or make it a float value like 0.5 to make it more blurred edge. Which is not that effective in my comment. So maybe after all, I might not need this distance. Yeah, maybe not. Maybe that was unnecessary things to do. So let's comment these out. Having less line of code might be better, so let's just comment these out. Okay, now starting to look good. And at this point you can like try to, if you want to have more of a random like values, you can add a different kind of seed to this one, or you can additionally add like another noise value based on the different scale of the C pause or pause, multiply by, I don't know, 10 something. Let's see what happens. Some more randomish values. Randomish morphing will happen. It really depends on what kind of morphing you're looking for. But I'm gonna make it simple. I'm gonna go with these setup. Looks good enough for me. Now, that is for the that is when you have only one source geometry, but the goal here is to morph from one geometry to the goal geometry, the target geometry, like these. So let me show you how you can actually do that using the same technique written here. I would like to go from this pig to this rabbit toy somehow. So I'm gonna connect. I'm first going to create a geometry and then have the same number of points. Well, it doesn't really have to be the same number of points, but it is better to have the same number of points if you want to use the whole number, the every number of points right here to morph it to the target points, and then randomize the point order. So to make the point number the same, I'm going to copy this parameter and then just paste it right here. Right? And also let's move this revertoid to the same position of this pick target in terms of the center point. So I'm gonna move this somewhere around here, make this a little bit bigger like these. Okay, looks good. Now basically what I'm going to do is pretty simple. I'm going to calculate the same rotation and the movement. This is the rotation, this is the translation for the peg head. But what I'm going to do is to do the same rotation, same translation to this point set as well. Okay, and then I am going to just lerp from or interpolates from the first point set to the target point set based on the frame values again. Okay, pretty simple. So let's try to do that. Okay, so I am going to delete these, delete this one. And to do that, I do need to get the point position from the second input. Okay, so let's first do that. I am going to the top, going to retrieve the point position from the second input at the same point number. Now there is a chance that the different number of points are supplied for the first input and the second input. So to make sure that all the points is going to be used, I'm going to calculate the remains based on the total number of the points from the second input. So in this case, in this way, even though you have more points on the first input, you can somehow use all the points from the second input, and if it goes over the maximum points from the second input, you can restart from point number 0 and use that for the target for the remained points. Okay. Now that you have got the point position from the second input, I do need to retrieve the minimum and maximum y value for this target geometry as well. Okay, so pretty much I'm going to do the same things I did here, right here, for the second input. So I am going to name the second set nmin and nmax, and use the get bbox from the second input for nmin to fill in the nmin and nmax. Okay. No, so if I have these values, then what I need to do next is to have the same things that I did for the first source geometry. I need to create the offset values for the second target geometry as well. So basically I'm going to copy these two lines and create another offset for the second input for the target geometry, and let's name this n offset, using the point position from the second input, which is npos and nmax, nmin, y, and the gradation range you can just reuse the same one. So I'm gonna keep it like these, and offset is the random of npos multiplied by the rand offset parameter. Okay, so now I have two random offset value, or frame offset value. Okay, like these. Now, next thing I would like to do is to somehow use this n offset value for this f value and where I should change. And to do that, the place I need to change is the target offset value. Currently I have offset value for the first value, source value for the fit, and the target value for the fit function. Now for the target fit function, I would like to change it to the target geometry. So this is where I should change this offset value. So I'm just going to add n, and I'm just going to change this to n offset so that the offset value for the target geometry is going to be used for this target value for the fit over the frame value. Okay. Now let's go down and see where I should change. And the next thing I need to do is to do the similar transforming like I'm doing for the source geometry right here, the rotation and translation. I'm going to do the same transformation for the end pause, the position retrieved from the second input as well. So end pause multiplied by the matrix, and then end pause add direction, just like this. All right. Now probably currently I'm just using the center point from the source geometry. So if you want to, it might be better to create a center point for the second geometry, for the target geometry as well, if you want to make it more based on the target geometry center point. If the center point of the first source and the second target geometry is different, then you might want to create a different directional value for this one right here. You might want to calculate a different center point. In that case, vector and sen is get bbox center from the second input, and then let's see where I'm using those center. Where is it? Which is somewhere around here, this one, direction. Okay. So I can just say, I can copy this one and let's rename this to n direction, and n pause subtract by n sen, and all the other value is same. Now this noise value is also based on the current point positions, so maybe I can also make this based on the second target geometry. So n noise value is n pause. The c pause is based on, again, the current point position, so let's have nc pause and pause. So I'm gonna change this to NC pause. Alright, so looks good, and I am going to add this and direction to the end pause. Now, visually you cannot see it yet, but what I did is to modify this target geometries or target position, target point position, just like I did for the source target. Source geometry, source point geometries. Okay, so meaning I have two set of points moving like these. Now what I need to do is to lerp between those two geometries, going from the peg head to the rubber toy by just using the lerp, going from the current point position, the source point position, to the end pause using like f, which is in between 0 to 1, to change the value. Okay, and let's set it as the current point position. And let's, if I play it with this, comes from pig head to rubber toy, like these. Okay, and if I move this to the X direction, I just think it should still work. Now I'll let a bit of weird rotation happening. But basically, it should work with any geometry at any positions. If I change this to some other test geometry, like, I don't know, squab, should still work. Let's select these. Okay. Looking good. Now if I try to change some parameters that I have set, let's say like the rotational cycle to like 4, you have more rotations to change from one geometry to another. If you change the rotational offset, you have more dissolved gradient edges. If you make it smaller, you have a direct change. The morphing gradient change will makes it be able to set how much of the frame is used to dissolve or to move from top to bottom. Okay, if you just make it like 0.1, most of the geometries or most of the points is going to be moved at the same time. And it's all done procedurally, so you can just go back and forth in real time without like generating any like simulations or anything. Okay, so I think that's the good part of this setup. Okay, I think I have a problem with my mouse. It's not. Let me. Okay, my mouse is not moving right now. Let me check the battery. Okay, somehow it's moving. Maybe I need to clean this up a little bit. Let me take this ball out. Okay, so I hope you get what I meant here on how you could create this kind of a procedural turbulence morphing effect from one geometry to another, which wasn't that hard, I believe. Oops. Okay. Yeah, I think. And now let's try to make it a bit more prettier by having creating some trail edge trail for the rotation, and also make these moving particles with a sphere or something. So first of all, I'm going to create a trail using a trail node. And let's have this like 5 or 6. Let's increment to 0.5 polyline. Maybe that's too long. Okay, maybe that's too long. Let's make it 0.1. And also let's have the points which is going to move as a sphere. I'm gonna make it as a polygon. Make it 1 frequency. Make it really small. And let's pack this as well. And then use copy 2 points. Okay, I cannot see it, so let's raise it up. Okay, and Alright, maybe the point is a bit too big. Okay, and if I play it, looks good. Maybe I can increase the trail length a little bit bigger. And let's also set the color of the trails based on the point number on the primitive. Just gonna get the point numbers from the primitive, and then set some value for the coloring as an attribute to each of the point. Set point attribute 0, let's say U, at PTSI with the I divided by the float of length BTS minus 1. Okay, now I am going to color these points based on the U value. Do I have this color? I'm not sure. Let's make this blue. Okay. Dark blue. Needs to be light blue. Let's just keep it white. Okay, just like that. And if you raise up the end frame like 200, you have more slow moving frames. And since you have a noise related values, you are seeing some turbulence like moving in between the morphing, during the morphing. Which is interesting, I guess. And if you go back to the code, the main code right here, you could probably add some additional like noise value. Maybe for the angle, to have a little bit more differentiated angular speed. To do that, you still need to make this as a multiplication of 2 pi at the first frame and the end frame. So what you could do is to, let's say, add angle. Use the same technique that I use right here, using the sine function to create the wave. And then multiply by some random related values. So rand at p, or yeah, at p is fine. At p multiply by the radians of 60 or something. Let's see what happens. And then I am going to add this angle to this one. So in the first frame and end frame, this add angle becomes 0, so that the end frame always will be the multiplication of 2 pi, but somewhere in between the 0 and the last frame, you have more randomish angle right here, which will create a bit more randomized speed rotation, which could be interesting. Is And without this add angle, let's see what happens. If I multiply with 0, this is without the add angle. And if you multiply by, I don't know, by 1, let's set it to like 120 degrees. You should be able to have a bunch of different angular added to the points to make a bit more of a different speed turbulence particle movement. Yeah, I guess I like this. Alright. Okay, I think I have a question from Sailpate. What's the reason for the pack SOP on the sphere? The reason is because to make the previewing faster. Without the packing, it's become slower because you are having all these geometry be calculated for the transformation. But by making a pack geometry or pack instance, you only need to calculate the single point transformation for each packed transformation, so makes the preview much faster. So that's kind of a reason. Since I'm just using the same sphere for all the points, doesn't really matter if I pack it to make it an instance. If you want to like deform the point position of the sphere, then you cannot use this pack. But if you're just using this constant sphere as a the moving particles, then maybe just using pack for those tons of points might make sense. Okay, so this is pretty much it that I wanted to show today. Only maybe as an additional thing I could show you is how I could switch between this pig head and rubber toy and go to the, since for the first frame it uses pig head at this point, and the end frame it changes to the rubber head, but from the next frame I might want to change the first frame. I might want to change the first geometry to the rubber toy and then go to the pig head on the next frame or for the next target. So switch between these two geometry based on the timing. First time you have a source as pig head as a source and rubber toy as a target, but next time you calculate the simulations, you might want to have a rubber toy as a source and pig head as a target. So let's see how we could do that. And to do that, I believe you cannot just do it with a VEX code, but you have to have some kind of I don't know, the external coding like Python or something. So if you are interested in that kind of stuff, I could try to do that as well. Use the Python to switch those source and target based on when it has reached, based on the count number of how many times it reached to the end and to go back to the first. Okay. So this is just a tryout that I'm gonna do now, which I'm not sure if it's going to work or not, but let's see. But basically what I wanted to tell you, what I wanted to show you for the turbulence morphing is just it just is done like these, and this is all this stuff that I really wanted to show for this week's tutorial. Okay. And if you find these things interested, I'll appreciate if you could like the video, and I will upload the created file later to this video description page of this live video, so you can download the file from there. I'm gonna do that as soon as I finish this live tutorial. And if you like to support me, then there's also a Patreon page of mine, which you could also go from the video description page. So if you could support me, I would also appreciate a lot. Anyway, let's try to switch the geometry using a Python. Yeah, I like this stop motion as well. How's that? Looks good. Alright, okay, so the things that I'm going to use is to first create a Python node, connect it to the end, and I'm going to name it as count up. And this one, and what I would like to test out is to how many times it reaches, the current frame has reached to the end, okay? So as soon as the current frame reached to the end frame, which in this case 200, then I would like to have a global variable of the Python to be counted by 1, okay? And I want to use that global count value to somehow use it for the switching variable to determine which comes which for the source geometry. Okay, so the first thing I need to do is to check the current frame value and the end frame of Houdini. And I am not sure how you can get the global variable of this Houdini from a Python. So what I'm going to do is to, if you know, please let me know. But since I don't know how, or maybe there's a way, but what I'm going to do is to create a channel to have the value that I would like to retrieve, which is the current frame and the frame end. And let's also have a integer parameter named as count, which is going to be used to switch the geometry. Okay, now the current frame, since this is a channel, I can just use this expression like $f, which gives you a current frame value. And for the frame end, you can also use the $f end to get the current frame end value. And inside Python, you can have these value using who dot eval param to get the frame from the channel and the frame end from the channel. Okay, now, and what I want to do and what I want to create is the condition: if the current frame is equal to the f end, then I would like to count these value up by 1. Okay, and I think I can just count this value from the evaluation. Maybe I don't really need to create a global variable after all. So to do that, first of all, I would like to create the conditions. If the frame is equal to f end, then first thing I would like to do is to get the integer value from the count parameter. So just like I did here, count is equal to count, like these, and then I'm going to add the count by 1, increment by 1. Now I would like to update this channel by this updated count value calculated right here. So to do that, you first need to access to the parameter object, which is named as count, and then set this count value. Okay, now this should work. If I play it, And if it reaches to the end, hopefully the count will raise up by 1. Okay, if I stop the simulations, the count become raised up by 1. Now, while I'm playing, it doesn't really show up the counted up values in real time, but hopefully this is changing. Even though this is not visually effective, if I stop it, you can see the counted value like right here. So probably I could use it on real time as well. Not sure. Let's see. Okay, let's reset this to 0 and let's copy this parameter. Copy this parameter. Going back to right here, and I am going to use this switch node to switch between these one. Okay, like these. So for this one, I'm going to set it as 0, and this one is going to be set as 1. If I set this 1, you get the rubber toy. If I set this to 0, you get a peg head. Okay, like these. So what I want to do is, as soon as you have count value raised up by 1, you want to change this input, selected input, to the different value. If it was previously 0, then you want to change it to 1. Then if it's previously 1, then you want to change it to 0. That's what I would like to do here, based on this count value that I write here, okay, which I have copied. So let's see if I could do that. First try, I'm gonna just paste the count like these, and for the second one I'm going to add by 1, okay. And then what I would like to do next is to, let's see, calculate the remains by 2. This one as well, calculate the remains by 2. So if the count is equal to 0, then for this one you get 0, for this one you get 1. If the count value is equal to 1, then for this one you get 1, you get 0 for this one, and then becomes at 0 in the next frame again. Now let's see if this is going to work. First change to the from rubber toy to, okay, I think it is working, isn't it? Yeah. So rubber toy to peg head to rubber toy. Yeah, I think it's working, isn't it? All right. That was easy. Okay, since this is working, I might be able to switch between multiple number of objects. So let's say I would like to add like the third geometry. Okay, connect it like these. In this case, maybe I could calculate the remain by 3 and see what happens. Okay, finger crossed. Starting from peg head to the rubber toy to a squab, and squab to, okay, it did work. All right, that was easy. Okay, so that's just it. You can use this Python code to create, I don't know, the modify the channel itself, just have channel value itself to have this conditional switching based on the how many times it reaches to the end. Which I am not sure when. I cannot really imagine the situation when could this be useful, but it's just a play. So just the proof of concept. Okay, so that's probably just it. If you have any questions, let me know. If not, I would like to end the streaming at this point. If you have any idea addition to the one that I have shown here, I would love to try that out. If not, let's just end this. I think I really do like the effect that I've created, like these. Let's try to make this color a little bit vivid. Well, just black and white is fine. Yeah. Since this is really a simple setup, you can try to modify these numbers by yourself. Maybe you can try to modify the axis for the rotation by yourself to see a different kind of morphing, which could also be interesting. Currently, I'm just using the y direction as a rotational axis, but could be any. The rotational axis can also be randomized as well, which could be really interesting as well. Maybe I would like to try that out as a last time. Where is that? This one right here. Okay, so I'm currently just using the y-axis, but you can try to randomize this one somehow. Maybe using the axis with the noise function, probably based on the point multiplied by some speed or smoothness of the value, and then divide by 0.5 for x, y, and z. Oops. And then use this as a rotational axis and see what happens. I'm not sure if it's going to be good or bad. Okay, I think I'm missing something. I think I am missing something. Not sure where. Doesn't really show where that is. Okay, axis. Is it right here? Set 0, 1, 0. Nope. This one. Nope. Okay. I am lost where I did wrong. Okay, let me just go back to where I have added the axis. Okay. Let me recreate the axis. Axis, set the noise at P, multiply by 2. Axis, set 0.5, 0.5, and 0.5. And replace this rotation axis with this one and see what happens. Oops, wow. Okay. Interesting. Maybe I should make this a much higher value. Right. Maybe it's not that good as I thought. Nope, not really. Maybe what I could do is to based on, it's pretty much based on the y-axis, but just add a little bit of noise to it, and that might give you a little better result. And let's normalize this. So basically it is y direction, but adding a little bit of like noise on different direction, which in result gives more y-oriented but turbulence like rotation. Okay, yeah, I like that. 5 multiplied by 0.5. Yeah. Yeah, I like it. I like the setup. Alright, looks good. Okay, that's probably it. Okay, so thank you all for watching. This is all that I would like to show, and I would like to do another weekly tutorial next week at around the same time as well. So if you are interested in this kind of thing, this kind of algorithmic design stuff, then please try to join and give me any feedback you felt would be very appreciated. Okay, so I'm gonna upload the files as soon as I end live, and you can download for the video description. Okay, so thank you all, and see you next week. Bye.